I will be interviewing Dr. Randara Pulukkody. Dr. Randara Pulukkody is currently working at DOW Chemical Company in the United States as an associate research scientist. Very good afternoon, madam.
Good morning, Himesha.
And I warmly welcome you for today's interview. Thank you for giving your valuable time for this interview today. Let's start.
Sure, thank you for having me.
Okay, madam. As the beginning, I would like to know about your school life. Was science your favorite subject from your school days?
Yeah, so this is a good place to start. So I completed my entire schooling career at Bishop's College, Colombo. Science certainly was among my favorite subjects, but I thought I'd mention I really also enjoyed the languages and literature as well. And we can talk about it later, but I think these subjects gave me a lot of other skills to succeed in a scientific career. But coming back to your question about science, yes. So even as a young child, I think I was curious about things. My mother was a science teacher, so I had that influence as well. And I still remember, I don't know in which grade, but after learning insect morphology, coming home and starting to collect cockroaches in a glass jar to see what happened to them over time. So this is not recommended even as a child. You should not be doing this kind of thing. But I think starting from a young age, my interest in science started to show. And then moving along to sort of the O-levels, I remember my O-level science teacher probably had the largest role to play in the decision I took to follow the A-levels in the bioscience stream. I still remember some of his science lessons. And then in the A-levels too, I really enjoyed chemistry. I still remember my industrial chemistry lesson and biology too. A lot of those things I enjoyed. So to answer your question, yes, science was one of my favorite subjects from school days.
Yeah. Next, I would like to know about your development as a scientist. How did you develop as a scientist? Was there any incident that inspired you to become a scientist?
Yeah, so I think like I said before, I think scientific curiosity was always there, but I'll be honest with you, when I chose to follow the bioscience stream at A-levels, my goal was to get into medical school. But I was fortunate to have had someone in the family. So my aunt was someone that had followed a similar career path in research. So I had a feeling for what other opportunities were available if I did not make it into medical school. So I mentioned this because I think it's important for anyone going into the A-level bioscience stream to think about, here are some other things I could do if I miss making it to my top goal. So I didn't think too much about becoming a scientist until I came into the Faculty of Science at the University of Colombo. And that too, I think the last 2 years of the special degree program, especially that fourth year research project, which gives you a feeling for what scientific research is like. So that I think is when I really started to think about a career in research and pursue becoming a scientist. So no, I don't think there was a specific incident that inspired me, but I had someone in the family that followed a similar career path. I was fortunate to have had that person to look out for. Yeah, so I think this is how I ended up becoming a scientist.
When you were an undergraduate in the University of Colombo, you won the Justin Samarasekara Award for the most outstanding science student of the year. It's not an easy task in getting such an award. How did you work hard to get this award? Can you tell us what drives you to achieve such excellence?
Yes, so first of all, I did not even know that this award existed until it was time to apply. So I never really worked towards this award. My goal was to do well in the academic program. I worked hard towards that first class in the degree program. So academic excellence was my priority. But by nature, I was someone that enjoyed doing other activities as well. Even during school, I did a lot of other extracurricular activities. So in the Faculty of Science, I found these types of ways to follow these types of interests through the Rotaract Club. So I was an active member of the Rotaract Club of the Faculty of Science. I was a secretary of it as well. So through Rotaract, I was able to participate in a lot of different activities, community service projects, and then I played a key role in organizing the science faculty job fair, which was at the time called Future Challenge. I don't know what it's called now. So I remember looking for sponsors, looking for companies to come and interview on campus. And then I participated in the science faculty debating team. I was more or less the official compeer for batch events. So these are just some examples, but I participated in a lot of different activities while I was there. And I think together with academic excellence, these activities paved the way to the award. But I think you generally don't really need to work towards an award. If you do well and you enjoy what you do, awards will come naturally if you deserve it.
After completing studies in the University of Colombo, you chose the Texas A&M University in the United States for your high studies. Was there any reason behind choosing this university for your high studies?
Yes, so that's a good question. There were a few reasons. So I knew my interests were in inorganic chemistry. So the way I started looking for universities to apply to was to look at universities at a variety of different ranks, if you will, that had good inorganic chemistry faculty, that did good inorganic chemistry research, and A&M was one of them. So of the universities that I received offers from, A&M had the professors that I most liked to work for. So this is why I picked Texas A&M. And even outside of the inorganic division, there were other professors that I knew if I wanted to branch out, I could. May have heard of Al Cotton. So from the Al Cotton times, the Texas A&M Inorganic Chemistry Division is a very well reputed one. So this is why I picked the university. I have to say though, Dr. Dhammika Desanayaka, having had graduated from there, I could speak with Sir about the questions that I had about the university and the faculty, so that helped as well.
You got your PhD degree in inorganic chemistry. So I feel that you love inorganic chemistry rather than the organic or the physical chemistry. Am I correct, madam?
Yes. So I mean, I don't dislike the other two areas either, but I do enjoy inorganic chemistry a little bit more. So the reason for this, I started to think about it, and I think two key undergraduate courses. The organometallic chemistry course, which at the time was offered by Dr. Rohini, was one that I absolutely enjoyed, and the bio-inorganic chemistry course, which at the time was offered by Dr. Ramani. These two courses, I think, were really the ones that had me thrilled about inorganic chemistry and brought me to pursue a research area in it too. So then when I moved into A&M, I found Professor Marceta Darensberg is the professor that I worked for. Her work was very exciting. She was one of the pioneers in modern bio-inorganic chemistry, if you will. So she works on iron-iron hydrogenase type enzyme active site models. So I have to say, while at the University of Colombo, I also enjoyed biochemistry quite a bit. So in bio-inorganic chemistry, I think I found the perfect home, the perfect mix of inorganic chemistry and biochemistry. Yeah, so this is why I decided to continue research for my PhD in the bio-inorganic chemistry area. I just found metalloenzymes very thrilling. The fact that the active site of an enzyme could have a metal ion that does what it does was just very exciting for me.
Yes, madam. I found another interesting thing about you. You are actively participating in STEM outreach activities in the Philadelphia area in the United States. What's meant by STEM? Could you please explain briefly about this project?
Yeah, so it's not really a project per se, Himashi, but STEM stands for science, technology, engineering, and mathematics. It's a commonly used phrase in the United States to refer to outreach activities or community service type activities in this area. So what we do is really volunteering your time to go out into the community to try to encourage younger students, young kids to pursue careers in these areas. So I do this through two different groups. My workplace offers a group called the STEM Ambassadors. So we go out into local schools. It could be a high school, it could be an elementary school. You take out exciting science demonstrations, things like lava lamps or, these colorful activities out into schools, and you do these hands-on activities with the kids. So they get to interact with a real scientist, and they also get to see exciting chemistry happen through colorful demonstrations. So one other quite popular annual event in the Philadelphia area is called the Philadelphia Science Carnival or the Science Festival. So this is a huge open air event where a lot of different universities in the area, different companies in the area would come and do this kind of hands-on activity. And then so recently I've also started getting a little bit involved in the Philadelphia chapter of the American Chemical Society. So so this is the kind of activity that happens through STEM outreach.
Next, I'm going to ask about your research. Your PhD research was on di-nitrosil ion complexes. Could you talk a little bit about this work?
Yeah, so it's been a few years since I completed that work and moved away from it. But these ion di-nitrosil complexes were very exciting little molecules. They had an ion center that was bound to two nitric oxide ligands, and if you think about nitric oxide as a ligand, it can be a 1 electron donor, a 3 electron donor. It has non-innocent properties. So as a result, long story short, this ion dinitrosyl unit, these complexes are usually called DNICs in short, so I'll call them DNICs from now on. They have very unique electronic properties. So what I did for my PhD work is to first learn how to synthesize them. They could be pretty air and moisture sensitive at times. So learn how to put these together, and then I also did a variety of different reactivity studies on them. And then I also did some structural modifications of these molecules to try to make them a little more biocompatible, with the final goal of trying to use them as nitric oxide releasing therapeutic agents. So I guess if I think about the types of skills that I gained through my PhD training, now my current job does not involve DNICs at all. I've moved completely away from this area, but the skills that I learned, if you think about the technical skills, I learned how to use air-free technique, how to prepare air and moisture sensitive molecules, isolate them, purify them. I learned spectroscopic techniques in characterizing these. I learned X-ray crystallography also as a characterization technique. And then, just to think about real world application type structural modifications. So when I did the structural modifications on them to improve their biocompatibility, that was a genuine idea coming from how can I make these more biologically relevant. So in short, that is what I did for my PhD work.
Yes, ma'am, it seems to be an interesting research project. My next question is about DOW. DOW is a leading chemical company in the world. You are a member of that company. Could you tell us a little bit more about DOW?
Sure. So I think to do justice to what DOW is, I will bring up a couple of slides. If that's okay, let me know when you can see my screen.
Yes, madam.
Okay. So DOW is one of the world's leading material science companies, belonging to the chemical industry in general. And it's a company that likes to say we're working towards solving the complex challenges that the world is facing today. But this slide really introduces what the company is to you. It's present in 31 countries, over 100 manufacturing sites. It's about a 35,000 employee company. And then if you think about the financial value, it's about a $43 billion company. So I wanted to start here because there are some things that I like to point out when working in a global company. There are skills that I think you can start developing from now on to do well in this kind of atmosphere. Okay, so if my slides move forward. Right, so this again is just to show you, when I say it's a global company, the global reach. So it is present in the United States and in Canada, in parts of Latin America, large presence in Europe as well, and in India. Unfortunately, not in Sri Lanka, and then quite a bit of presence in the Asia Pacific region. But this is a snapshot of the kind of thing DOW does from a chemistry perspective. And I thought it'd be interesting for you to know how these types of chemical material science companies approach consumer markets. So if you think about the different classes of materials, what's shown here on the left are the types of chemical feedstocks, if you will, that DOW has access to, ready access to. So I'll not talk through all of them, but ethylene oxide, propylene oxide, you'd say EOPO, silicones, polyurethanes, acrylics, cellulosics. These are the kinds of feedstocks that are commonly used. And if you think about capabilities, there's robotics or high throughput research, catalyst discovery, ligand synthesis, polymer material science, and then the list goes on. And if I move over here, DOW has the world's leading position in the types of chemistries that are listed here as the world's leading supplier. So again, I'll not talk through all of these, but you'll recognize some of them. Again, things like propylene oxide, solvents, ethylene copolymers, acrylic acid, and so on. And then all of these different feedstocks and chemistries are used to develop ingredients or products that go into very broadly 3 different markets. So DOW serves in the plastics and packaging area, the infrastructure area, if you think about things like building construction, and then construction chemicals. And then I'm a part of this 3rd pillar here, which is called consumer solutions. So we can talk about it later, but consumer solutions can be anything from household care, personal care, to electronics, and so on. DOW is very large in promoting sustainable solutions. You'd see this slide just kind of summarizes the sustainability goals that DOW has, focusing mostly on circular economy, protecting the climate, and coming up with safer materials. And then I thought I'll mention just a little bit about DOW R&D, because for your colleagues, if you were to pursue a career in research and go into industry, research and development is probably where you'll find the first home in. So large companies like DOW are typically structured this way. You have what's called business R&D. So you have groups that interface directly with customers in these 3 different regions. And then you also have what's called the core R&D expertise. So the scientists that work in this core R&D structure are really quite similar to an academic professor. They have deep expertise in their area of work. They get to do long-term academic type projects, and they interface very closely with the business research groups to deliver solutions to the customer. I also thought of quickly pointing out what high throughput capabilities are. So DOW is quite popular for promoting high throughput research. We have robotic tools to do state-of-the-art catalysis, synthesis type experiments, and then also formulation, preparation, films and coatings, that kind of thing. So think about the amount of time and manpower you can save through this type of setup, right? So we can do 16 experiments, 16 synthesis experiments in one go, for example. 16 is a small number, just a hypothetical number, but whereas a single scientist can probably do 1 at a time. And then DOW is also quite popular for the world-class analytical techniques that it has. So anything from separation to microscopy to surface science, anything you can think about, really, DOW will have the analytical capabilities for. So if you are an analytical scientist, it really is a great department to be in. DOW also has ready access to the US national lab capabilities in certain universities, and it's always been known for developing new analytical methods and introducing these to the scientific community. I am not a computational chemist, but there are experts in this field working at DOW. So lots of molecular modeling, fluid dynamics, that type of work happens at DOW as well. So I'll stop there. I could go on and on about DOW, but I'll stop there. I just thought I'll bring that up so you can see that, academia is not really the only route to do really good research. If you join the right company, the right atmosphere, even in industry, you can do some really great work as a scientist in industry.
As you said, you are specialized in the development and application testing of the new molecules for home and personal care applications. How do you think your research will help humans and the environment? Or what are the real-world applications of your research?
Yes, so one thing you do get, one thing that's a given when you work for industry is it has to be real-world application based. So what I'll talk a little bit about what I do in my current role. So as a synthesis chemist by training, I was hired into the DOW Home and Personal Care unit also to do new molecule development, design and development. So my job as a scientist, if you think about it in very simple terms, is to go in the lab and develop new molecules based on what the project requirements are. So DOW being this global ingredient supplier kind of company, we work very closely in the home and personal care group. We work closely with any of the large brand owners in home, household, or personal care. So just as an example, if you think about someone like Unilever, Procter & Gamble, and then if you think about in the cosmetics world, something like L'Oreal, Estee Lauder. So these are all customers that DOW typically would work with. And then based on customer requests and demands, we will then have new molecule development work happening. So my job is to take on requests like this and go in the lab and really design new molecules. And then we speak about applications development. What that means is you then take the new material that you made in the lab and start testing them in the real world application that you've prepared it for. And so this applications development piece is also very interesting because you sometimes have to come up with new methods for testing. And these methods have to be statistically validated. And then your product will go through the applications testing pipeline. If it's successful, then it'll go up through to scale up. So you have to then think about, it can't be just lab curiosity, it can't be outrageous reaction conditions, it has to be something scalable. So if it's successful, then it goes through to an intermediate scale up stage. And then from there, finally to the manufacturing plant, which is what you'd hope for. So when you take it to this chemical plant scale, the work that you did in the lab better be reliable. It should not have any safety concerns because it's now working at very, very large scale. And then finally, if you're successful, it'll come out into the market as a product. It'll be sold to the brand owners that we talked about. And it'll finally go into a product that you and I can buy from the shelf of a grocery store. So to me, that's really the most exciting bit of this. That's something that I developed in a lab setting, is then in a final consumer product that can be bought by anyone.
Yes. As you think, what has been your most important scientific finding or the most surprising finding up to now?
Yeah, so I'm sure you've spoken with people that have had long careers than I have. In my short career, and unfortunately, I'll not speak too much about my findings at DOW because of limitations that I have on disclosing that information. But genuinely, I think the most exciting finding during my graduate school work was I had this wild idea once sitting at a seminar of preparing this sugar-bound di-nitrosil iron complex. And the inspiration came from seeing this gold-bound gold molecule which had a sugar thiolate bound to it. So then I thought, maybe I can leverage that into these DNICs. Anyway, so I went in the lab, I tried this reaction. I could spectroscopically see that it went well, but I threw it into under a few different crystallization conditions. I did not expect to see crystals because this is a complicated sugar-bound structure. But I think I got really lucky. A few days later, there were beautiful crystals. And anyone that works in this area of inorganic synthesis would know what I mean. When you see crystals form from structures that you don't expect, it can be something that's really memorable. And I even took photographs of the crystals, and that crystal structure is printed and hung still in my office at work as well. So that was, to me, probably the most exciting finding. And scientifically, what it meant was it was the first step towards derivatizing this class of molecules. So I used a simple sugar in that case to bind to this di-nitrosil iron unit. But what it went on to show is if you have the right conditions, you can then think about binding polysaccharides. So instead of the polymer, I used a simple model in the sugar, but this was the first step towards derivatization to improve biocompatibility.
Let's move to when we're doing research, we have to face different types of challenges. According to your experience, what types of challenges did you have to address when you started this work?
Yeah, so if I think about challenges, I think I went into an area of research that I had absolutely no lab experience in. And this might be true to many of my colleagues as well. So I had no inorganic synthesis experience. But I was genuinely interested in that area of research, and Professor Darrensburg was a great mentor. She convinced me that with some training, this is not a big deal. So at the time, this was a big challenge in my head. I was concerned that there were undergraduates, people that completed undergraduate work coming into Marcetta's lab with experience in inorganic synthesis. And here it was, I hadn't even seen a Schlenkline until then. But, you know, I came to see that what's important is recognizing a challenge, navigating through it, finding ways to overcome it, and not really get thrown away thinking about it. The other challenge, I think, is anyone going into research needs to get used to failure. Experiments fail all the time. So for me, that was a little bit difficult to get used to. I had a lot of things fail in my first 2 years of work. So then you start worrying. I have this entire thesis proposal written. Nothing seems to be working out. What am I going to do? But I think, like I said, if you keep trying, if it's something you enjoy doing, you sort of have the will to keep going, right? And then talking to people about the problems that you're running into in your experiments, talk to people. I used to go into other labs and meet friends and discuss my research questions with them. So yeah, these were the challenges at the time. And like I said, I think if you recognize that it's a challenge, seeking help and not giving up helps you sort of navigate and find a way out of it.
My next question is about the future of chemistry. What areas would you think will be the future of chemistry, and why do you think so?
Yeah, so my answer is going to be a little bit biased to the type of work that I do in DOW. I think sustainability is here to stay. If we're finding sustainable solutions, sustainable chemical solutions to the problems that the world is facing today is the future of chemistry. It might be energy efficiency, like we talked a little bit about. It might be safer materials, maybe materials that can degrade better in the environment, maybe material of natural origin that you can end up using in final products. Greener ways for material synthesis. For example, I think biocatalysis in the pharmaceutical industry is catching on. So I think anything with a sustainability element attached to it is going to be very, very important for the future of scientific chemical research and scientific research in general.
Yes. At last, I would like to ask from you, what advice would you like to give to the students who are interested in the science and research?
Yeah, so I think, first of all, this is the time as an undergraduate, I think it's the time to build a firm foundation with strong fundamentals. So the theoretical knowledge that you're gaining is extremely important to set that foundation. But also if you are deciding to go into a career in research, it should be into an area that you really enjoy. Because otherwise, like we talked about, when things get tough, you don't have the motivation to keep going. But if it's something you love doing, then it won't become a burden anymore. But outside of these two things, I also thought I'd mention a little bit about the soft skills side of things. So whether you go into, so the PhD needs to be thought of, I think, in my opinion, as a short-term goal. This is not the end of it, right? You get a PhD to then move on to the next stage. And for that next stage, it's very important that you develop certain soft skills. And this includes skills like teamwork, leadership. So at DOW, for example, in my current job, I'm expected to be the lead scientist and lead teams of scientists. So my leadership skills are extremely important to be successful, and at the same time teamwork, because I am also a team player in certain project teams as well, and these can be global teams, so they're not all based in my workplace. Some people are based in different places in the United States, some people in different countries. So working with global teams, these kinds of skills can become extremely important. And then I think communication skills, scientific communication skills is extremely important, that you take every opportunity to develop that. It can be written communication, it can be oral communication. I think your expertise, your technical expertise will not have the right opportunity to shine if you don't improve your scientific communication skills. So I think people often overlook developing these kinds of areas as young students, but once you move out of that student mode and get into the workforce, that's when you realize, I need to really think about developing these kinds of skills. So starting early is always an advantage, and that I thought I'd mention as a piece of advice.
Yeah, ma'am, it's a very important message to all of us. So, thank you so much, madam, for allowing me to interview you today and giving your valuable time for me. We were spending memorable time with you, and we are very proud of you because you are a fellow Sri Lankan, as well as you are a proud alumnus of the Faculty of Science, University of Colombo. I would like to add my best wishes to all your work. At last, would you like to say something?
Yes, no, thank you so much for having me. This was it was nice to be a part of this program and think about, reminisce my times at Colombo University. So thanks for having me, and best wishes for everyone, and regards to all of my teachers that are still at the department as well.
Thank you so much again. So this is the end of my interview today. I'm Himesha Lakshani, an undergraduate in the Department of Chemistry, University of Colombo. Thank you all for joining with me. Have a good day.